Hallo, liebe Teilnehmer. Herzlich willkommen zur nächsten OOP-Keynote. Mein Name ist André Kollert von Sixdata.com, Veranstalter der OOP. So let's switch over to English now, and I would like to introduce you to Kris Jenkins from Confluent. Kris is a developer advocate for Confluent, a veteran startup contractor and former CTO and co-founder of a gold trading business. He started his career working for a finance company whose success depended on having a better data model than their all competitors. And the search for better architecture has been with him ever since. Kris' keynote topic is Side Effects Are the Complexity Iceberg. Just a quick information for the attendees. If you have any questions regarding the keynote, just go on the website slido.com and use the hashtag OOP Digital. We will then fade in the questions at the end of the keynote and try to answer as many as possible. And I think Kris and I are grateful to you when the questions are asked directly in English. So, Kris, welcome to our OOP conference.
Thank you.
Unfortunately, not in person, but digital. We are happy to have you here. And so,
thank you.
The stage is yours.
Thank you very much, Andre. Yes, hello. I'm Kris Jenkins. I am a developer advocate for Confluent. And in a way, I suppose I want to tell you why I'm working for Confluent, who are a company spun out of the birth of Apache Kafka. But where I really want to start, as so many great tech talks have started, is with an XKCD cartoon. If you really hate someone, teach them to recognize bad kerning. Kerning being the gaps between letters that you can go a whole lifetime never noticing, but once you notice them, badly kerned fonts and badly kerned signs are a painful thing to behold. But, you know, it's not all pain, because noticing little details like that can open up a whole world of appreciation for kerning and fonts and typography and graphic design. In a way, kerning is a window into seeing a much better way of doing graphic design. And that's what I'm hoping I can do with this talk, because I want to talk about something that initially is going to seem like a very small detail, and we're going to zoom out and out and out to get a much bigger picture about software. So let's talk about side effects. As developers, as software people, as systems builders, I think a lot of us, many of us, have a vague notion of what side effects are, right? Side effects are when you print to the screen, aren't they? Or when you write something to a database. Something like that. But we don't have a precise notion of side effects. We don't have a very usable notion about it. And because of that, I think we don't really think about side effects that much day to day. And it's a shame, because when you see the world through the lens of side effects, you can actually see a lot of why our systems get complex and a lot of what we can do about it. So when I started thinking about this, my first goal was to try and come up with a usable working definition of side effects that a programmer at the coalface can actually hold in their head and their hand and use to intuitively understand them. So let me put it like this. Let me tell you that every function you write has two sets of inputs and two sets of outputs. And you think, no, Kris, hang on, that's not right. I know about functions. A function has a set of inputs, that's called the argument list, and it has a singleton set of outputs, the return type, right? In fact, every function basically looks like this. I take a pair of ints and I add them together and I give you back an int. Well, no, that's not how software works. There is a hidden set of inputs and a hidden set of outputs in nearly everything we write that's interesting. Take a look at this code. Imagine a function that wants to delete emails by some search term. We give a regular expression to match the searches we want, or a more complex query. We find the matching messages, we delete them, and we return a Boolean, true or false. Did we delete some messages or not? It's easy to see the visible inputs and outputs, but think about the code. The inbox manager has a state, and the state of the inbox manager is absolutely an input to this code. The code completely depends on what that inbox manager state is at the time we call it, so it must be an input. Equally, the state of the inbox manager after we call this function is absolutely an output. We wouldn't bother calling this function at all unless we expected that state to change. So it's an output of calling this code. Let me give you one more example just to hammer it home. Let's consider a function that tells me what's on television at the moment. And I realize this example slightly dates me. I hope everyone in the audience can remember when channels showed programs just now and you had to see it or miss it. But imagine I give this function a channel ID and I ask it what program is on that channel right now. This code has two hidden inputs. One is our notion of now. Now is absolutely an input to the function, even though we haven't put it in the argument list, because it completely dictates the behavior of this code. And there's also this.programs, which is another hidden input. This value of this.programs will completely change what this returns. So those are real inputs. So let's start with this as a definition of what side effects actually are. Side effects are the hidden inputs and hidden outputs that a function secretly depends on. Doesn't declare them anywhere in the function signature, so they won't show up in the Java doc, but they are absolutely cause and effect part of the code we're writing. So what? Does that matter? Yes, it does. Let me explain why. So for a good way into understanding why this really matters, consider testing. How do we test some code like this? Delete by search term. Regex as input, Boolean as output. You can't test this code. You absolutely cannot test code like this unless you crack it open and look at the source. There is no way to check the behavior of this code without understanding its hidden inputs and hidden outputs. So what we do is we do test harnesses, right? We set up a mock inbox manager state and we inject it into the thing we want to test. And then we run the code that we actually want to test. And then we go back and look at the thing we injected and see if it's changed its state. But it absolutely depends on understanding the code we're trying to test. If you've got hidden inputs and hidden outputs, you cannot do black box testing. In fact, if we were going to make this some testable code that we could just look at the signature and test without understanding how it does its job, it would probably have to look like this, right? We would have to pass the inbox state as an input, and we'd have to somehow include the inbox state afterwards as an output. Now, you may look at this code and think, ew, that's suddenly got a lot more complex. It hasn't. It's exactly as complex as the code above it. The only difference is you can see the complexity. So this has a knock-on effect. It's not just about testing, because testing is just one way we use our APIs. But if our API, if our contract, if our promise to the caller doesn't include all the inputs and outputs, then they can't hope to use the code correctly without peering into it. They can't hope to set it up because they don't know what inputs to give it. And so you end up with that dance you often get in Java or JavaScript, where you try and configure something correctly and you get null pointer exceptions and you go back and you find the thing you forgot to inject at the start to configure it. And eventually you get it sort of working. And we get this problem on the output side too, where you kind of guess that a function called save user is going to write to the database or write to a file or save that user somehow, but you've got no evidence of that. It's just an assumption. And the other thing that hidden inputs and hidden outputs do, which is terrible, is they kind of make a mockery of this idea of reusable components and composition. In theory, we compose software by taking these little circuits, these little independent components, and wiring the outputs of one to the inputs of the next, and building up a larger chain of useful software. But it doesn't work like that. It works a lot more like this, where not only do we have to line up the inputs and outputs, but we need sufficient knowledge of the underlying code that we can hope to line up the hidden inputs with the hidden outputs. It's one of these things that sort of everywhere as systems get larger, this hidden complexity actually becomes a bigger issue than the visible complexity on top. We end up with a world of hidden complexity graphs in all our software. Now, what do we do with that, right? You could say, there's nothing we can do, right? It's part of programming that we hide some complexity and we show others. And a good systems designer makes good choices about what to hide and what to show, and that's the best we can do. No, most vehement no. We can do better. And in some parts of our industry, in some parts of our knowledge sphere, we are doing better. That's what I really want to talk about, because there's hope. But before hope, a bit more despair, because I actually think the rabbit hole goes a little bit deeper. And when I first heard about this, realized it genuinely kept me awake that night. I hope that one or two of you are kept awake by it too, which is a bit cruel of me, but I'm hoping to lead you to insight. So let's have a quiz. Have a look at this code. I have a piece of code that's going to take an array of things and add some cats to it at position 2, and then print out the thing at position 2. Simple enough, right? Well, what will this code print? You can assume the array list is sufficiently long that this isn't a null pointer question. What will this code print? Of course, you know it's a trick question. This code will print dogs at element number 2. Why? Because threads. But why? Why do threads cause this problem? Because think about that data. It isn't just data. Data itself has a hidden input. And the hidden input to all our data is the behavior of anyone else who has a reference to that data. If they have access to it, they can come in and change it. And suddenly, data, instead of just being facts that we have gathered about the world, becomes this shifting sand, which includes the opinion of anyone else who has access to it. It's kind of horrific. And it's not something that just shows up on threads. It's any time we share a reference to data. It's just that threads are the easiest way to see it explode. That should keep you up at night. We can't even rely on the data, much less the functions we're writing. So what can we do about it? And I want to pull on this thread of side effects and see a couple of different ways in very different domains that we can use the lens, the glasses of side effects to analyze and solve this problem differently. So let's start with something we know. One of our first techniques for managing this problem is to say, well, we can't eliminate it, but what if we put a wall around our data and a wall around the way we can change it and our hidden inputs and outputs, and we just said, I'm going to close around this data and you can only access it through a few very special ways, which I will allow. We build something like this. And you, as a user of my code, let me worry about all the side effects. They aren't really gone. They just become somebody else's problem. That approach we know very well. That's essentially what object orientation is. Put a wall around it, put an API around it. There are still side effects, but they are contained. Zoom out a bit. Take exactly the same pattern on a larger scale, and that's exactly what microservices are, or one way of doing microservices. Put a wall around it, contain the impact of this particular concern, and only allow people to access it through agreed channels. Somebody in the room is thinking Corba too. Microservices aren't quite as new as we think. Those are good solutions. Let me emphasize that I'm not taking anything away from those solutions. We've all built systems with them for decades. I've built some very successful systems with that style of complexity management. But it isn't the only approach. And when we add more ways of solving problems to our toolbox, we end up making better, more appropriate choices in the systems we design. So, what other solutions are there to this problem of hidden inputs, hidden outputs, moving data? One I think is quite inspiring is Rust. Rust concerns itself particularly with this idea that data can change under your feet, that data contains the hidden input of other people's behavior. And what it does is it takes who gets to write this data and it pushes it into the type system. It says data also contains an idea of who has write privileges, who has the access to it. And if I'm trying to change a data structure, I have to make sure that I'm the one that's allowed to change it. I have to be the one that owns that data. Otherwise, the compiler won't even compile the code. And if I give you a data structure, either you can only read it, or I give away my ownership rights, and I give away my right to change it. What's really interesting about this is that tracking this notion of ownership solves a lot of memory management and concurrency problems. But it's also this technique of taking the problem of side effects, pushing it into the type system where the compiler can get a hold on it for us. So we can start to build machines that track side effects. That's all I'm going to say about Rust. If you are building any systems in C or C++, I encourage you to take a look at it if you haven't already. But tracking the ownership of data is one solution. What if we went further? What if we went much further? What if we went really hardcore on data and said, people aren't allowed to change data under my feet. If I have a list of 3 things, you can't just change that while I'm not looking. You can take a copy of that list and do what you like with it. But once this list is set as the 3 things I received, it's set for all time. If you pull on that thread, if you pull on the idea of eliminating side effects from data, you get immutable data structures. And your APIs start to change. We can no longer add cats to a list. What we do is take a list and add cats to a copy of it and return that. That is something that started to come into Java recently, relatively recently. And it starts to change the way we program, right? Some people complain about this. They say, oh, copying lists all the time must be desperately inefficient. That's not true. We've known how to do this efficiently for about 20 years, and we've been iterating on that idea and productionizing it. It's a good idea. It helps keep the data we're standing on stable. In fact, appeal to authority, it's officially a good idea. Oracle says so, so it must be true. Maximum reliance on immutable objects is widely accepted as a sound strategy for creating simple, reliable code. But I think we've got an advantage over Oracle here, because I think we now know why it creates simpler code and more reliable code. It's because our data can't move under our feet anymore. Not only does it change the way we do APIs, but in a way it opens up data. This wall we've put around our data to keep it stable, we no longer need to hold on to quite so tightly. We might choose to put a wall around data for things like data protection, privacy, security, but that's different. When we do that, we're protecting the data for its own sake. We're no longer, what we don't have to do anymore is protect the data just to keep it stable enough, to manage the side effect of other people changing it while we're looking. We can start to build systems where the data is available to other people to run their own calculations on. And I'll talk about that more in a minute. But brief diversion. While I've mentioned Rust and the changes to Java, let's just have a look at one more programming language and consider, what about other side effects? It's not just data we need to track. There are other side effects we need to worry about. So I'm going to briefly tell you a little bit about a language that has thought a lot about this for the past 20 years, which is Haskell. Haskell does a few tricks to manage side effects. The first thing it does is it says all data structures are immutable. You cannot change data under my feet. Go create your own copy. The second thing it does is it says there are no hidden inputs. If a function relies on an input, you must declare it, except for constants, which are considered compiled into the world. And the third thing it does is it accepts that there are some outputs which are inevitable, writing to a database, and it tries to constrain those in the type system. Let me show you how that works. So we're just going to have a quick look at a bit of Haskell syntax. It's not too scary. It's just a small part, I promise you. Start with my function add cats. It takes a list of things and a position to add cats to. I don't know why I'm obsessed with cats, but the whole internet seems to be. Firstly, we take out the word public. Haskell has the idea of public, but not the keyword. And we take out the variable names, and we get something like this. Then, something I've always thought was very sensible, we move the return type to the end, which always made a lot of sense to me. A function, you give it some things and you get this result at the end. And then we do a little bit of syntactic sugar, and voila, we've reached Haskell. You can read that last bit exactly the same as the first bit. To add cats, give me a list of strings and an integer, and the last thing in that list will be the thing I return, a list of strings. Okay. With that knowledge, we can see a trick that Haskell pulls, which is interesting. This function, delete by search term, it takes a regular expression, the inbox state, and returns a Boolean, did we change it, and the new inbox state. Actually, I wrote this code, and I thought we could easily refactor that. There's a better way to do this. Why not just return the inbox state if it's changed and return nothing if it hasn't? But if you look at that code, this world in which we're returning the inbox state, maybe, and just try and think slightly differently. Think of optionality not as a structure around inbox state, but a context around it. Think of the function signature like this. Give me a regular expression and an inbox state, and I'll give you a new inbox state back in the context of it may or may not happen. I may or may not change it. By doing that, by pushing the idea of context into the type signature, we can actually do some really interesting stuff. So let's have a look at this code. Imagine I want to register a user. Give me a username and a password, and I will give you back a new user in the context of having access to the database. Suddenly we can pull in these side effects into a place where the compiler can help us track them and keep tabs on them. So consider this code. I want to calculate tax payments, right? I've got a list of transactions. I give you back an amount. And I want to record a tax payment with, I don't know what the German equivalent is, but over here it's called Her Majesty's Revenue and Customs. I give you a user ID and an amount of tax I want to pay, and I'll get back a receipt from the government. And I can only do that in the context of having access to the internet and having access to logging, right? So now I come along and I try and compose those bits of code into a handle tax function. I say, you give me a user ID and a list of transactions, and I'll give you a receipt. But the compiler complains. It knows this isn't enough. To generate a receipt, it's going to complain that you're calling a function that needs access to the internet and access to logging. So it tells you the only way you can compile this is by declaring those side effects in your higher level function. You cannot get away with hiding side effects anymore. This has really interesting practical benefits. Imagine that the internet is down, right? I can look at just the API, just the contract it declares to me, and say, well, if the internet is down, calculate tax payment will work just fine. It doesn't need the internet. Record tax payment is suddenly going to fail. I can track which side effects change the behavior of my code and know just by looking at the docs what's a problem. Does that seem academic? I don't think so, because imagine suddenly one day we find that there's a critical security vulnerability in logging systems, which I think you'll find fairly believable these days. I can look at my code and say, well, handle tax is affected because it needs the side effect of logging. Record tax payment is affected because that needs the side effect of logging. But I know that calculate tax payment isn't affected. I don't need to retest it because it never relied on that system. So I can start to see the impact of side effects across my larger system and get automated, disciplined, tireless help from the computer to do so. So I think Haskell is very interesting by pulling side effects into the type signature and leveraging the compiler to help you. I felt I should stop at this point and give a quick controversy warning. Am I coming into a conference called OOP and telling you all to learn Haskell? No, I'm not. I'm not doing that. What I'm saying is twofold. Firstly, we have a great tradition in our industry of finding ideas from other places and stealing them. Stealing in the sense that Picasso approved of taking good ideas from other places and using them in art. And I think that's something we can do, and we do. We've been stealing in the Java world ideas from functional programming for quite a while. Lambdas, stream processing, immutable data structures. There are more ideas here to steal. And the other thing I think is useful is if you're interested in learning, in sharpening your lens for side effects, then I can think of no better way to do that than to enter an automatic training room that is Haskell. It teaches you to spot side effects and it doesn't let you off the hook until you can see them. So I think that's really interesting. Anything else? Anything else? Yes. One more thread I want to pull on before we go to Q&A. And I like this thread because up until now, we've kind of gone deep down into the nitty-gritty of programming. But this is a thread that kind of goes broad and affects how all our systems work across the board. So consider again one of our lists, for instance. Consider a list of transactions in the system. How did that list of transactions come to be? We started off with an empty list and we gradually added transactions to it, right? And maybe we took some out or reversed some. But we got there by things happening and us changing this data structure. So think, what is the state of a system? The state of a system is really this data structure, which we may or may not be able to see depending on our walls. But it's not just data, is it? It's every piece of state is really data that has the hidden input of the history that caused it to get in that state. And you can actually start thinking on this hidden input of history and pull on that thread. And it will take you, I think, in two main directions. The first main direction I think it takes you in is state machines, right? These are not a new idea in programming. They are, in fact, one of the oldest ideas, right? This idea that you start with the state and things happen that transition you into a new state. Very old idea. Alan Turing would have recognized this idea. But I think it's coming back into vogue for a good reason. That if you've eliminated side effects from your data, then you've eliminated side effects from these facts that come in from the world. And your state machine is the thing that changes. Before you've got immutable data structures, the state machine changes and the facts can change too. And it's kind of not really worth having a bunch of data that can change and a summary that can change at the same time. But when the facts are immutable, they're just permanent records of what happened. Suddenly it's worth thinking about systems as facts and state machines again. If you pull on that idea in the domain of front-end programming, Eventually, you're going to reinvent Elm, which you may not have heard of, and React and Redux, which were directly inspired by Elm. This idea of treating user interfaces as a series of facts, a transformation over those facts, and then a way of looking at that summary, that state. Equally, if you take the same idea and do it on the back end, maybe in the world of DevOps, you might end up reinventing something like Docker. You maybe have to squint to see it, but if you look at a Docker file, what it is a starting state and a series of facts that will transition that starting state to the end state you're hoping to get. What I find interesting about Docker is if you and I start with the same state and we have the same list of facts, we can run those lists of facts and end up at the same ending state, which means we actually don't need to. I could build that final state once and share it with you. And that's how Docker files work. If you've got a starting state and a pure transformation based on facts, then you can share the result. You can share it at any point along the chain and we'll end up with the same thing. If you're interested in DevOps and you want to pull on that idea further, go and take a look at Nix, which pulls this to the nth degree for repeatable, binary compatible builds at every level of granularity in the system. That's all I'm going to say about that, because what I really want to get to is the other side of looking at state machines, which is almost an economic question, I think. Why do we throw that history away? Why do we take it and use it and transform our state and then throw it away? The answer is we don't always. People in the accounting world have known for years that you don't throw those initial facts away, even if you're computing a balance. A balance may be the most important question you can ask of the facts of a history of transactions. But they're still facts. They don't stop being true just because you've added them together. You keep them as a permanent record. And you find, if they're a permanent record that cannot change, you find other interesting uses for that same data. So you find that maybe the facts that generated a balance today generate a tax report tomorrow and generate a budgeting question. So you can see where your money was spent the day after. I know where all my money was spent. It was spent on synthesizers. That's a confession. But the fact that we have these stable facts that we can reinterpret in different ways changes the way we do programming. And lo and behold, we've just invented this idea of event sourcing. When you realize that these facts are actually quite expensive to acquire, a user interaction is not easy to get to. Ask any startup that's looking for its first user how much money they've spent to get to that point. But holding on to those facts is suddenly now quite cheap and reliable to store. I think state machines and event sourcing are having this kind of renaissance, if you like, because we've hit that tipping point. We've hit the technological tipping point where we can rely on the data being stable, and we've hit the economic tipping point where it's cheaper to store data than it is to acquire it. So, event sourcing is perhaps the last thread to tug on, but let's tug on it just a little bit longer. Let's talk about databases. How do modern databases do replication? If you think about that, you'll pop the whole thing open. My programming career kind of begins when they were doing it badly, and databases like tried to handle replication by copying individual rows at a high level, or by copying blocks on disk at a low level. And it's hard, and it never worked that well. And I think we can see now why it never worked that well, because it's hard to copy a piece of data when, to understand the data completely, you have to copy all the behavior that goes into it, all the people that have access to it, really. And you can't do that. So you copy the data and it's changed. That doesn't work for database replication, and everyone figured this out quite a long time ago. And what they all do now is they treat it like a state machine. They do replication by when you're about to change the state of the database, write what you're about to do to a log, append-only log, and then roll forward. And replication becomes as simple as, like in a Docker file, it becomes as simple as me sharing this log of all the things that have to happen to a starting state, you running over that with the same state machine and ending up a precise replica. That's, to my knowledge, that's how most all modern databases do replication. But what if we built a database like that from scratch? What if we started with a database that concerns itself with capturing just the facts and then worries about manipulating them and summing up state along the way? We would expect replication to be very cheap and easy. Other databases have proven that for us. We would expect to be able to build up a very sophisticated state machine. Other databases have already done that. They started from the other end of the chain, but we could start from this facts and transformations system. If you do that, you're going to end up reinventing Apache Kafka. And I think this is why I work for Confluent, because I'm very interested in seeing how these ideas of side effects play out on the broader landscape of systems design. Because an individual block of code changes the way you program, but the way we store and manage data changes the whole organization. And I think what you find, if you start building the systems this way, if you start pulling on that thread into systems design, you end up with a world where the database looks quite different, but it's moved into this world where you just have a series of facts and a machine that draws conclusions from them. And anyone can look at those facts and draw different conclusions. Our accountants can draw one conclusion, our balance system can draw another, our user analytics can see how busy people are making transactions, all looking from the same data that we don't need to guard so desperately anymore because it cannot change under our feet. Maybe we go to a third party and they give us some new facts, which goes into a new place in the database. But what we really end up with is, I think, a simpler system of more open data. We can protect it for privacy reasons. We don't protect it for complexity reasons. And then machines of the right level of complexity processing over that system of data. We get lots of nice things for free if we do this. We get lovely properties like replication is cheap and easy. We get things which I might get in trouble at work for not mentioning, like this is an excellent way of doing real-time systems because you can look at the leading edge of facts transforming over time. But what really excites me about this is the opportunity to make a stable platform of data and simpler transformations on it, opening up that data into what amounts to a very different style of microservices, in which data is not clamped down, but transformations on it are. If you go down that route, you've reinvented this idea of data mesh. So, lots of ideas we've reinvented, lots of ground we've covered. I hope at least some of them have tickled your interest. But let's sum up. Let's talk about side effects once more. In 2006, there was something of a classic paper published called Out of the Tar Pit, which introduced me to this idea of essential complexity and accidental complexity. Every system has some essential complexity. If you want to build a system that tracks, processes tax rules, in the UK at least, that's really complex, and nothing you can do as a software developer or a systems architect will make the tax code, the tax laws simpler. That's essential complexity. But there's also this idea of accidental complexity. The things we don't mean to make complex as programmers, but we have through the systems we build. And a big source of that is hiding complexity, hiding inputs and outputs in a way that they still affect us, but we can't see it anymore. We have solutions. We can bring these hidden things to the surface and manage them in different ways. And I think if you pull on those threads, I hope that if you walk away from this talk with one thing, it's learning to spot side effects. because I think you'll reinvent lots of these ideas in whatever domain you work in. But if you're already excited by one of these ideas, maybe you've just discovered immutable data structures, maybe you're looking at repeatable builds with Docker, I hope you'll see how the sudden rise of that way of thinking actually has a unifying, connecting idea, which puts everything in context. If you're not in that headspace, and if you think things like microservices and data mesh and event sourcing and functional programming and immutable data structures, if you think they're all fads or just fashion or the changing popular way of doing programming, they're not. There are fundamental underlying reasons why our industry is changing in that way. And if you just hold on to the idea of hidden inputs and outputs, you can find it for yourself. And I think on that, I'll end with questions.
Kris, thank you for this interesting presentation. So let's have a look at Slido and the questions. Let's have a look at the first one. Doesn't it break encapsulation principles to pass everything as input parameters?
I would say no. Encapsulation in a way is building this wall, right? And saying these things can change under the feet of a function, but it's my problem. But that's one way of looking at encapsulation, right? It's what's the best way of expressing this? Encapsulation is about hiding, but hiding actually isn't necessary to do good code. Hiding the things, that's what I need to get to. Sorry, I'm getting there slowly. Encapsulation should hide the how. It should not hide the what. If code depends on something as an input, it's okay to hide how you use it. That simplifies coding for other callers. It's not okay to hide the fact that you need it because you're going to need it. The caller somehow is going to have to set that up for you. That's not hiding. That's not encapsulation. That's just making things harder to find.
Okay, thanks for that. Next question. What are your thoughts on implicit and explicit state or fact management? Most businesses processes can be reduced to a state machine. Should they?
I think, okay, let me tackle those separately. Implicit and explicit state management. I think there are places where there's still a judgment call to make on when do you capture all the facts and when do you throw them away. If I was building a front end that captured this stream of facts and wanted to reanalyze it in various ways, which I have done, I still wouldn't capture all the mouse movements. That's too much data, right? That's data I don't really care about. But user clicked on a thing and it worked, user clicked on a thing and it didn't work. That is in my judgment call, interesting data to keep hold of that may be useful down the line and is actually quite manageable to capture. So I think you have to kind of make a judgment call on which data is valuable. And we're moving that line further and further as the cost of doing so gets cheaper and easier. Most business processes can be reduced to a state machine. Should they? They kind of are anyway. If you start looking at software through the eyes of state machines, they kind of really are. I mean, the state machine is kind of a universal model. The only question is how clear is it to see the state machine? And I think it ends up with clearer code if you go into that model with your eyes open. It can be a very good tool for structuring code.
Okay, next one is not a question, but I really advocate if you want to encourage people to use immutables. JavaScript devs does this with the Redux pattern and it works very well.
Yes, absolutely. I will throw into that. if you are interested in learning Haskell or doing some front-end stuff, have a look at Elm. It really is worth your attention. One thing it does is it has immutable data structures by default. It does a lot of the big tricks of Haskell, and it's very user-friendly to get started with. So if you want to play around with some of these ideas at a language level, Elm is a very nice way to get started, and it will let you build some good websites.
Okay, next one. Set of concerns. If details have no be carried in from the outside, then yes, there are no hidden details, but on the downside, there are no hidden details.
I'm slightly going to have to guess what that question means. Separation of concerns. Usually, I think separation of concerns implicitly includes hiding the availability of data. So you get systems where you've got a user registration system and you're using it to track users and track, I don't know, it manages passwords too. And one day the people from marketing come in and say, we'd like to get some analytics on user registration. Or the people from the UX team come in and we want to say, why are people failing to register? If you separate concerns by saying, I own all user information ever, then the only way they can do that is by coordinating with your team. If you separate concerns by saying, the data is available to our organization and I'm just going to concern myself with a particular kind of processing, then you open up other departments to processing the data in their way, keeping their concerns separate, but not forcing them to interfere with your concerns just to get access to the data. And that's really the heart and soul, I think, of data mesh, if you've come across that idea.
Okay, next comment. Great quote from Oracle. Given that a classical database is a huge mutable object.
Yeah, yes.
Okay, and I think the last one, another comment. I would bet that 60% of developers had at one point in their career stumbled over to some kind of kerning-related bug like new line detection.
Yes. Randall Munroe really hit a nerve on that. I read yesterday, actually, Randall Munroe has a new book coming later in the year, and I'm just going to plug that because I'm a fan.
Okay, let's have a look at the time. We're a little bit over time, but Kris, thank you. No problem.
Thank you all. Thanks for listening.
So, greetings to London and all the best.
Farewell, Germany.